Okay, so now that you've considered this, well, if we can draw a blue marble, well, it has to be, we have to be in this row, right? And then a red marble, well, it has to be either this event or this event. So this event here would be sort of blue, red, would be blue, red 1, blue, red 2. 'Cause those are the only ways you can get first a blue, then a red marble. So the probability of drawing a blue marble, then a red marble is going to be um, 2/9 because it's just the number of elements in the sample in the event, which is 2 over the number in the sample space size, which is the number of boxes here, which is 9. Okay, now here's one question. You can still see this in view. What's the probability of drawing, a little grammatical problem there. What's the probability of drawing 2 red marbles? Okay, I'm going to pause recording. I've answered. Okay, so just there was a question, just to comment that events are sets, probabilities are fractions, and the connection between the two is the probability is the number of the size of the set, which is the event, divided by the size of the set, which is the sample space. So the fraction you get is dependent on the size of the events, which is a set. Okay, so the question was, we were considering is what's the probability of 2 red marbles? Well, we get the answer by just looking at all the outcomes and seeing that there's 4 squares in the upper left-hand corner that are the only ones that have 2 red ones. All the last column and the last row all have a blue marble in them. So the probability is going to be 4/9. Hopefully that's what you guys got. Now, here are 2 sort of more general questions. What is the probability of drawing either a blue marble or a red marble? That is in the you've drawn, you go through the whole process of the person drawing the first one marble, then a second marble, and what's the probability of drawing that you get either a blue marble or a red marble? That's actually sort of it's actually E red union E blue. So, well, let's look and see. If the event where you get a red marble is almost all of them. It's everyone except for this one, and this includes the blue one. So really every outcome has either a red marble or blue marble. So the probability is going to be which equals 1. So that always happens, right? Because it turns out that this is the sample space. So but it fits with the formula that you've got the number of outcomes in the event. Something happened, either red or blue, and it's just a different way of sort of stating, is defining a set that is in underneath happens to be the sample space, but maybe is a little hidden at the beginning. So this means this always happens when you get a 1. Okay, and then what's the probability of getting neither a red marble nor a blue marble? Well, I'll give you a moment to. Okay, well, we're having a set where there's neither red nor blue, so our event here is equal to the set of all the outcomes up here that don't have a blue marble or a red marble in them. Well, they all do. So this is the empty set. Therefore, the probability is the number of items, the number of elements of the empty set divided by the number of elements, the sample space, which equals 0/9, which equals 0. So the probability of drawing either a red marble or blue marble is um, 0. Okay, so we have a question um, for, oh, maybe this is a little bit obscure. This is not a 5. This is an S, which equal, maybe it's a little bit clearer. Is that Oh, in C. Okay, good. I think it my my S unfortunately looks like a 5, and hopefully that'll well, it still looks like a 5, but I guess you can tell. Okay, well, that is let me export this with and I'll put that up on Piazza, so you can go either do the answers with the blank or go over it. And so that's basically reviews what we've done last time and how you apply it in certain cases. Um, and what we want to do now is begin looking at this is sort of like the topic next week, conditional probability, but it's still it's a little bit oh well maybe before that um, there's a let's contemplate again maybe we could do a little project here. Let's look at the birthday puzzle. This fits in with it's not conditional probability. So the puzzle here is um, let's say we have a group of people. For example, there are I think 13 people registered in CS 205 this semester. So the question is, what's the probability that two of these people have the same birthday? Well, that seems like a hard problem to figure out, and so we have to we have to simplify it to make sort of an idealized form. Is first of all, we um, want to apply um, the standard probability. So we have to find some event. So our event would be that any two of these people have the same birthday. Well, we have to sort of begin to get a handle on that. For example, the birthdays. Well, it could be like January 1st, January 2nd, and we can label all the days of the year up to 365. So we can ignore leap years. That's, there's a like every 4 years, unless under certain conditions, not completely every 4 years, but every 4 years that's um, up to some, there's some sort of special cases that where you don't do this, but do you have a February, an extra day in February, so there might be 366 days. So, okay, but we're going to just ignore that. And so consider people that are born on that their birthday is one of the numbers 1 through 365 days. So we're going to assume, and this is actually incorrect. I mean, we're going to assume that all days equally likely for a birthday. Well, it may be that in um, that certain days are going to be more the people are there's probably a distribution that more people are born in the spring than the fall or something like that, or different seasons. And but we're just going to ignore that and say that all days are equally likely. So the question is, how can we sort of get a handle on this? And this 13, we're actually going to be interested not just 13, but any group of n, because we're going to want to know if you have n like one or two. If you have two people, well, let's just do the special case of n equals to 2 and see what's the probability that you just take any two people and what's the probability that they have the same birthday. And this will maybe help us to get warmed up um, for doing this problem. Well, the I have two people, and you can think about it like this. This first person could have any of 365 days of the year. They're equally likely if we didn't know. So if we just choose two people randomly, there's 365 different ways they could have, um, you know, um, a birthday. Now, if they weren't on the same day, the second person could also be born on any of 365 days. So what's the sample? Well, the sample space size is going to be a number from 1 to 365 times a number from 1 through these are born independently, presumably. So the sample space size here is going to equal 365 times 365, which we can write as 365 squared. And we can see then if n was 3, it would be 365 times 365 times 365. So it'd be cubed. So we could predict or think that the sample space size in general, this is for 2, this is for n, would be 365 to the nth power. So in our class, it would be 365 to the 13th power, which is a pretty big number, but that's our sample space size. Okay, but now we want to count what's the event for n equals 2, the event that they have the same birthday. Well, that would mean that the possible outcomes would be 1, 1, 2, 2, like January 1st, both born in January 2nd, both born on January 3rd, both born on January 4th. So you can see that the number of these, maybe we have to put a dash between these to sort of, because we're going to get multi-digit numbers. Well, you can see that the event of same day is going to have the number of elements in it is going to be 365. Okay, so what's the probability that two people have the same, just randomly selected two people have the same birthday is going to equal 365 over 365 times 365. We can cancel off one of the 365s. So the answer is going to be 1 over 365. Okay, well let's look and see what happens if we had n equals 3 people. Well, we'd have sort of 3 people that with any, this is sort of the sample space sizes, 365 times 3, this is cubed, not squared. Now, the problem is that there's going to be like, then we want to count the event of same day. Well, what kind of elements are there going to be? Well, the first one here, like this, this first person could be in any of 365 days. But then the problem is that the second person could, if like one of these two, well, there's lots of different possibilities. For example, this first person could have the same birthday as this person, and then this person could have the same birthday as this one, or these two, this person could is with the other two. So there's many different you'd have to sort of select out. Well, you'd have first, second, third. Well, the first and second could have the same. The first and the third could have the same. The second and third could have the same, or they could all three have the same birthday. So there's lots of different possibilities. Now, because of this, it's hard to do this number, but there's a trick. What we're going to use is the principle of exclusion. This is more of a counting problem, the principle of exclusion inclusion that we talked about in counting, where it's simpler to count for the number instead count number of people with no number of situations with no one having same birthday. That's the crucial trick that you want to sort of get involved with, because then, like for the n=3 case, we could count how many ways are there for 3 people to not have the same birthday. Well, this first person could have any of 365 days. And then for the second person, well, they could have any day except the one that this is on. So there's really 364 choices for this one. Now, the third person could have, well, they can't have whatever day this was. They can't have whatever day this was. So they only have 363 choices. Now, this number begins to look like something you've seen before in counting when we messed with this of the factorials and sort of extended this so that this number here would look like 365 factorial over, well, this one that you're multiplying in would be 364. 362 rather. The first one that comes after this, 362. 362 factorial, which is the same number. So we could put this in, and then this is the number that so the probability that they don't have the same birthday. This is the event not same day. So the probability of the event that they have the same V day, or at least 2 of them have the same V day, would be the total number of situations. That's the size of the sample space minus the number where they are different. So if we subtract off the number where there's no, if we take the total number of situations here, which is this up here, 365 cubed, and subtract off it this number here, and then divide by the total number of ways of people having birthday, then that's going to give us the one with the same birthday. So we can get by with counting this number here, which is much easier to count than to count the other one. Now, what the puzzle is, which I'm introducing to you here, we're not going to solve it completely, or I'm going to let you solve it for next time, say, is this first probability puzzle. And so I go through and I talk about the one with 2 people here, and then here is the idea here is that what you want to do is, in the end, to calculate the probability, you actually need WX maxima to get the number. And the idea here is we want to find what's the probability 2 people have the same birthday for n=15. That's like our class size. Without n=30. Then the question is, what's the smallest value of n for which the probability is greater than 0.9? Well, that would mean that that's like a 9/10. If you do statistics, that would be 90% of the people time. If you had a group of n people, you want to know what number of people do you have before there's going to be 90% of the people will times there'll be 2 people that have the same birthday. This has been used by the fact this number is a lot smaller than you think can be used by speakers in an ice-breaking event in which they get everyone to put their birthday, not the date, but just like February 15th or January 2nd. They put that in a piece of paper and they take it, and they're almost guaranteed that they're going to find 2 people that have the same birthday. And so that's some kind of, anyway, it has some kind of use in that sense. But what I want you to do is think about this puzzle and see if you can um, i- begin to come up with some way of dealing with it, which is the same, which is an extension of this case, because for the n equals 3 case here, the probability for n equals 3, same birthday, is going to equal the sample space size minus the number in no same day divided by the sample space size, which is going to equal, if I can divide this in, it's going to be 1 minus e no save, not the same day, over the sample space size, which is going to equal 1 minus, and then we have this thing up here, which is the 365 over 362 factorial, 1 over 365 cubed. Well, the question was, wouldn't this be over 100%? Well, let's look and see. How we could do this in Wx maxima. So this number here is, you can see, is 365, 364, 363, and let me show you how to do this with a function. P of n, or P of, say, capital N, then use a colon. Now, we could have 1 minus, and then we could do 365 factorial divided by 362 factorial. But then we want to do times 1 divided by 365 cubed. Oh. Oh, there's no n here, so we can just there. Okay, so it looks like the numerator isn't larger than, essentially what you have is here, you have 365 divide, if I was to write this out explicitly, this is going to be 1 minus 365, 364, 363, 3 over 365 times 365 times 365, and let me clean that up a little bit so I'm not being completely illegible. Okay, this is 365, 364, 363, 365, 365. Well, the 365s would cancel. You have 364 over 365, 363 over 365. And so the number here would be this number here. And then if I want to see the actual number, which I do here, you can go up under numeric and toggle numeric output. Then if I come up here and press again, I get the fraction. So the probability that 3 people have the same birthday is 0.008. That's like almost just 1%, like 8/1000ths, which is about 1/100th. So from Wx maxima, this number is approximately equal to 1 over 100. So it's pretty rare. Okay, so let's